to do is give y'all a screencast for the short lesson that we have on kinetic molecular theory and pressure. And this is for lesson 1.8 and the beginning of 1.9 as well. So before we start really talking about pressure, let's start off by talking about kinetic molecular theory. And kinetic molecular theory, KMT, helps to explain the constant motion of gas particles. And KMT is based on 5 assumptions. And these 5 assumptions all are dealing with an ideal gas and not a real gas. And why? This helps to simplify the calculations a little bit, and it also makes gases a little bit easier to understand. So let's go through these 5 assumptions. First of all, the first one is that gases consist of large number of very tiny particles that are very far apart, and so that the volume of most of where these gases are contained is actually empty space. Assumption number 2 says that the collisions between gas particles and between particles in the container wall are elastic collisions. So once again, this is for an ideal gas. And one way to think about this is like if you have a bouncy ball and you let that bouncy ball go. So it's not that you forcefully push it down, but you just let it go down. You just drop it from your hand. You will notice that every time the ball bounces back up, it doesn't bounce as far up as the previous time. So that is an inelastic collision because some of that energy is lost to the friction between the ball and the floor. But in an ideal gas and in KMT, we say that all collisions between these gas particles and each other and with the wall of the container that they're in, that they're all elastic. So there is no energy lost to friction. The third assumption of the kinetic molecular theory is that gas particles are in continuous, rapid, and random motion. So all gas particles move in straight lines, but it's very random. Where they hit, or what they don't hit, it is all just continuous and very, very random. The fourth assumption, there are no forces of attraction between gas particles. So once again, we don't lose any energy. It always has elastic collisions. The collisions are continuous, they're rapid, they happen in straight lines, and they are random. And there are no forces of attraction between the gas particles. Once again, remember, because we are dealing with an ideal gas here, there is no forces of attraction between these gas particles. In a real gas, there would be some attractive forces between gas particles, but for what we're dealing with, there are no attractive forces. And the fifth assumption is that the temperature of a gas depends on the average kinetic energy of the particles of the gas. So all particles of the gas at the same temperature have the same kinetic energy. Okay, so once again, in an ideal gas, we're saying that every single one of those particles in there that are at a particular temperature have the same exact amount of kinetic energy. Because remember, temperature is really about the average of the kinetic energy, but not with KMT. In KMT, with our ideal gas, we're saying that all particles that are at a particular temperature all have the same amount of kinetic energy. So now that we've gone through like the 5 tenets of KMT, let's go ahead and talk about pressure, because pressure and gases really go hand in hand with each other. And pressure is the number of collisions of particles, and for this we're just going to say with gases, with the inside walls of the container. Now, as a mathematical expression, pressure is force divided by area. And we've all experienced pressure all the time. Probably one that I've talked to y'all the most about is tire pressure. And we've said in the past that when it gets to be one of the very first cold mornings of the year, we find that lots of times when we get in our car, the car tells us that our tire pressure is low. And that's because we have less force between those molecules. And so we see in our top picture here where we have very low pressure in the tires as compared to the picture at the bottom where we have normal inflation and normal pressure for those tires. So if pressure and force have a direct relationship, what we see with pressure and area is an indirect relationship. An inverse relationship. And this is probably experienced a lot in terms of shoes. Pressure equals force divided by area. So this is kind of similar to the idea of density equals mass over volume, where we see that same type of relationship between pressure and force as we do in density and mass. Pressure and area, the same type of relationship as we see in density and volume. So what we see is that the smaller the area becomes, the higher the pressure is. The larger the area becomes, the less pressure there is. So that's why with a high heel shoe, we have much greater pressure underneath that heel as compared to our snowshoes up at the top of the picture here, in which that snowshoe is supposed to distribute a person's weight evenly over that entire area so that we have less pressure on the snow, and that way the person in them isn't sinking as much in the snow. So pressure is dependent on three things: volume, temperature, and the number of molecules present. So if you wanted to increase the pressure, what would you do to the volume? Hopefully you said to decrease the volume. So what we see here is a very inverse relationship between pressure and volume. If you want pressure to increase, you have to decrease the volume. And then, of course, if you want pressure to decrease, you need to increase the volume. Temperature. Once again, we go back to those tires on the first very cold day of the year, in which we see that we have this direct relationship. As temperature decreases, so does pressure, because we don't have those particles hitting each other with as much force, and therefore not hitting the sides of the container, in this case a tire, as much as either. Number of molecules present. So once again, if we want to increase pressure, another way that we could do this is by adding more molecules, which is what you do when you get that low tire pressure light on and you go to the service station and you go get your tire filled up. You increase the number of molecules present in order to increase the pressure in the tires. All right, so it's really, really important that you understand the relationship between pressure and these three different factors. We also have atmospheric pressure, and this is also really important. The atmosphere, which is a shell of air surrounding the Earth, exerts pressure. Objects at sea level feel a greater atmospheric pressure than objects in the mountains. And when I say objects in the mountains, we mean pretty high up here. Whether that's, let's say, the Rocky Mountains, or if you really want to get really high up there, even Mount Everest. And it's important that when we're talking about atmospheric pressure, what we're really talking about is the gravitational force on a column of air. And when you are at sea level, that is thought of as being one atmosphere, or in the other unit of pressure, 101 kilopascals. So both of these atmospheres and kilopascals are very common units for pressure. But once again, don't forget, this is like a column of air pushing down on a surface or a person at, let's say, sea level. Now, barometers are a very useful tool, and it's used to measure atmospheric pressure. And when I am done with the screencast, it would be a really good idea for you to watch the video that I have here on how the barometer was invented. It's a very interesting story. It won't take very long to watch. And then follow that, please, by watching this video on how a barometer is used to predict the weather. But here is an example, an illustration of a mercury barometer. And what we have is a glass tube, and the glass tube is filled with mercury, and you invert it, but you put your finger over the top of it, you invert it, and then put it into the dish of mercury. And this allows for a vacuum to be created up at the top. Atmospheric pressure is going to press upon the mercury that's in our glass dish and causing some of that mercury to rise in the glass tube. And once again, when you are at sea level, it is going to rise to 760 millimeters. And of course, if you are higher up in the mountains, we're going to see that that isn't going to rise quite as high because there is less pressure the higher you go up. And then there's more pressure the lower you go. So if you could go lower than sea level, much lower than sea level, you would see that you would actually get the mercury in the glass tube to actually go a little higher. So as I said before, once you are done watching the screencast, please make sure to watch these two videos. They're not very long at all. Okay, so I had already told you that there are some different units of pressure, and it is really important that you can convert between our different units of pressure. So what I want you to pay attention to is right here. So this is all of your important conversion factors that you might need. The mmHg, this is millimeters of mercury. TORR, TORS, this is for Torricelli, which when you watch the video on the making of a barometer or the history on how barometers were made, you'll find out where this unit comes from. PA is for pascals, and that's the SI unit for pressure. And then we have kilopascals, which is probably used a little bit more often than just pascals, just because pascals tends to be such a small number. I mean, a small unit, so the number itself tends to get very large. So in order to keep the numbers where it's a little bit more understandable to the mind, we tend to use kilopascals. And then PSI, pounds per square inch. This is really just used mostly in tire gauges for your tires or even bike tires. So let's try to do a couple of conversions between the different units just to make sure that you understand how this works. Okay. So let's convert 3.4 atmospheres to kilopascals. So what you're going to do is write 3.4 atmospheres, and we are just going to put that over 1, and we are going to then put our conversion factor next. Don't forget, we should always have, well, not always, but for this particular problem, we should have atmospheres at the bottom and what we are trying to convert to at the top. which in this case where you're trying to convert to kilopascals. So let's see what our conversion factor is. So for every 1 atmosphere, you have 101.3, and let's just leave it at 101.3. Most sites, most books don't use the 2.5, but just 101.3 kilopascals. And so what we see here is that we have a pretty simple multiplication problem. Don't forget, just check to make sure that everything is in its proper place by canceling out units. So since atmospheres is both in the numerator and in the denominator, we can cancel them out. This leaves us with just kilopascals, which is the unit that we're supposed to be solving for. So then you just have a very simple multiplication problem. So I'm going to use the calculator on my phone to say 3.4 times 101.3, and you're going to come up with 344.42. But don't forget, we need to look at our significant figures. Our original measurement had 2 sig figs, so underline, look behind, and this is going to give us 340 kilopascals. And as always, we should box our final answer. All right, let's try the other one. So for the other one, we have 275 millimeters of mercury, and we want to convert that to atmospheres. So I am going to make sure to have my millimeters of mercury in the denominator, and I'm going to have my atmospheres up at the top. So my conversion factor shows me that there are 760 millimeters of mercury in 1 atmosphere. And once again, I'm going to make sure that I have all my numbers in the correct spots by canceling out units. Millimeters of mercury, cancel out millimeters of mercury. This leaves us with just atmospheres, which is what the problem wants us to solve for. So once again, we're going to do a real simple, in this case, a division problem. 275 divided by 760. And this is going to give us 0.3618, and then it just keeps going on. But for sig fig purposes, we're doing good here. So our original measurement had 3 sig figs. So I'm going to underline that third significant figure, underline, look behind, and this is going to become 0.362 atmospheres. And of course, I'm going to box that final answer. All right, so that is what you need to know for right now on pressure, atmospheric pressure, how a barometer works, how to convert between all the different units of pressure, and also about the 5 tenets of the kinetic molecular theory and how they relate to an ideal gas. And I will see you later.